Alright, today we're going to talk about vectors and scalars. First of all, scalars are just quantities which have magnitude only. Magnitude is just a fancy word for size. So for example, speed is a scalar quantity where the car is traveling at 45 meters per second. It doesn't give any indication of the direction or distance of 5 miles. Again, no directional component. Vector quantities have both magnitude and direction. So they have a magnitude, a size, and a direction. So a couple of examples of vectors. Velocity is a vector. So we're traveling at 45 meters per second at 45 degrees north of east. So again, the difference between speed and velocity has a directional component. The difference between distance and displacement is that displacement has a directional component, the due east. A vector quantity can be represented on a graph where you have x and y axes that represent directions. So if we have a graph set up, we're going to call this east, west, north, and south. Pretty standard. We use arrows to represent vectors, and the length of the arrow represents the size or the magnitude. And the vector sum of two or more vectors yields what's called the resultant vector. So let's do some vector addition. So if two vectors are pointing in the same direction, so if we look at our homework assignment, we look right here. Let's look at number 2. See how these two guys right here are pointing in the same direction? Well, that means that we can add them together and take the sum of those two to get one resultant vector. So in this case, we get a total of 130 meters. We add the two together. So if we look at our notes, the resultant vector is the sum, which means addition, of the individuals. Then it gives an example here. On a hiking trip, you travel 10 miles north. And 20 miles north on the second day. And 35 miles north on the third day. What's your vector displacement for the 3 days? So if we add them, sort of like this, where they're all going north, and we have 10, 20, and 35, we get a total from here to here of 65 miles. And again, the direction would be north, which is shown by our arrow. Let's look at the second one. What if they're pointing in opposite directions? Well, it's going to be subtraction, or the difference in the two. So it says the tires push off the road with 27,000 newtons of force in one direction. The car experiences frictional forces of 11,000 newtons from air resistance and 9,000 from the road. So let's draw our car. Pushes off the road with 27,000 newtons. So we can show that. Again, it pushes on the road pushes back on the car, so it's now trying to accelerate forward. And it's going this way, so we can draw little swishies behind it to show, oh, it's moving in this direction. We're pushing on it with 11,000 newtons of force from the air and 9,000 newtons from the road. So we have 27,000 forward and we have 20,000 in reverse. So those, and this would be, if we're drawing it like to scale, this would be a lot larger than these two, and these would be actually closer together, etc. But you can see what is our net result of that. So that's going to be the same as showing at 7,000 Newton force in that direction there. And we could call this a positive 27,000, and we could call these negative to give us a positive 7,000 newtons. Essentially that's what we got, where this direction is the positive direction. Let's look at the next one. So now we're going to add vectors at right angles. So first we're going to align the vectors tail to tail. We're going to form a square, or actually more of a rectangle, from the two vectors, and then draw a line from where the tails connect to determine the hypotenuse. So you'll see what it mean in this example here. So we've got Carl Yastrzemski that's hitting a baseball at 50 meters per second due east. So we're going to draw a vector there. The ball experiences a wind blowing 5 meters per second due north. So again, tail to tail. Okay, if we look at an arrow, this is the head, this is the tail. So we're putting them tail to tail. This is 50.0 meters per second. This is 5.00 meters per second. And then now I'm going to draw a rectangle. So to do that, I can draw like a dotted line to make my rectangle. And then I'm going to draw on a hypotenuse to show what the resultant of those two are. So it's going to come off at some angle, which we're going to determine. And if you notice, how long is this side here? What is the magnitude of this side of my rectangle? Well, it's the same as this side right here. And what would the magnitude of this side be? It's going to be the same as this one down here. So I can make a right triangle out of these vectors and find an angle. So essentially my right triangle would look something like this, where here's my right triangle, this is the angle I'm trying to find, and I know that this is 50 meters per second, this is 5 meters per second, and this is my resultant. And this should bring us back to what we did in our trigonometry. We have a right triangle, we have a side, or we have an angle here that we're trying to find, and we have a couple of sides. The first thing I'm going to do is find this angle. So how am I going to find that angle? Well, I know the opposite side of the angle, and I know the adjacent side. So that function is tangent. So tangent of my angle theta is equal to the opposite, which is 5.00 meters per second, divided by the adjacent, which is the 50.0 meters per second. So theta is the inverse tangent of this value, and if I plug that into my calculator, I have 5 divided by 50, and take the inverse tangent of that answer, and I get an angle of 5 point, and then I look 3 digits, answer's going to have 3 digits, so it's 5.71 degrees. Now, how do I give, okay, that's great, 5.71, but then I have to give it a little bit more indication as to where it is. If I look at my axis, my coordinate system here, this axis would be called what axis? This would be the east axis. And our angle is 5.7 degrees what of that east axis? It is north of east. So that's how we label this, north of east. Okay, let's do another one. Let's say my angle is this one, right over here. Well, what axis is it connected to? It's connected to the west axis. So this would be south of west. How about this one? What's it connected to? It's connected to my north axis. So this would be west of north. So hopefully that helps you with where this came from. Again, we are north of the east axis. If it helps you, put axis at the end of it. North of east axis. So there's the direction. How are we going to find the magnitude of it? Well, a couple ways. One is you can use Pythagorean theorem. A squared plus b squared equals c squared. That's one method. The other method is to use this angle, and then you could use sine or cosine to find it. It's really up to you. Pythagorean theorem is fine. You got to watch your significant digits, but I'm going to just show you an easier rule on that. So r is equal to the square root of a squared plus b squared. R is equal to the square root of 50.0 meters per second squared plus 5.00 meters per second quantity squared. And I'm going to let you do all this in your calculator. So we're going to kind of cheat here on this addition rule. Really, this is a multiplication because you have a squared. This is a multiplication rule, you have a squared. Then you have an addition rule, and then you have to take the square root, which is like a division rule. So quite a bit in there, and I'll show you the difference between it. So if I do 50 squared plus 5 squared, and then take the square root, I get 50.249. Again, I'm going to round to 3 digits because my two numbers are 3 digits. So this is actually going to be, don't double round. So this isn't 50.25 and then round it to 50.3. What's the number right after the 2? It is a 4, so we round down. So 50.2 is the answer, and it's in meters per second. So there's the magnitude, and there's the direction of this. Okay? Final part. We're going to now determine the component vectors of a vector. So when this vector is at an angle, we're going to have a horizontal x component and a vertical y component. So let's look at our notation here. We have 90 meters per second at 30 degrees north of west. So again, set up your coordinate system. North of west axis. North of west axis. So here's our west axis. We're going to be north of that by 30 degrees. Okay? Everybody see where that came from? What's the magnitude? 90 meters per second. How do we get this vector? Well, we can break it into a vertical vector and a horizontal vector. See where those came from? If I added these two, I get this one here. Again, look at your rectangle that you made from before. See how that makes the rectangle? So I had to go up and I had to go over this much to get it to go to this way. Or essentially, I just make my right triangle and fill it in, where this is my x component and this now is my y component of that. Should look familiar for a right triangle. Here's my right triangle, my hypotenuse, here's my angle, solve for the x and y. And use sine and cosine. X is what side of my triangle? Hold my angle here, this would be adjacent, so I'm going to use cosine. So cosine of 30 degrees is equal to the adjacent, x, over the hypotenuse, 90 meters per second. X equals 90 meters per second times the cosine of 30 degrees. Plug that in my calculator. I get 77.94 meters per second. Again, round to the right number of digits. 2, this should be 30 point right there. So this is going to round to 2 digits, so I get 78 meters per second. Ooh, what am I missing? Good, a direction. What direction is that pointing? West. Don't forget that, like I did. So that's your x. Let's look at the y component. Y component is the opposite of that. So it's really simple. If this was cosine, this is sine. If this was sine, this is cosine. It's just the opposite trig function. So sine of 30 degrees is equal to y over 90 meters per second.